Okay, another argument based. So 0.01 moles of nitrogen and 0.1 moles of hydrogen and 0.4 moles of ammonia were inserted into 1 decimeter. So their concentration would be as its same amount of moles because 1 decimeter. So you're going to divide the concentration to find the concentration. You're going to divide the number of moles by the volume. So volume is 1 dm means, so the concentration will be equal to the amount of moles. So it was allowed to reach equilibrium at 500 Kelvin, and the equilibrium is given, and they have found the equilibrium constant as 2 into 10 to the power 2. Give me a second again. Which of the following statements is correct for the changes in the system from the initial stage to the equilibrium? QC is reaction coordinate. So, okay, so I have explained this to you before. When a reaction becomes equilibrium, at the beginning, there will be higher concentration for some components, lower concentration for some components. So for an example, in our reaction, it says this is 3H2O, this is 2NH3. So here we know for ammonia, the concentration is 0.4 m. Hydrogen is 0.1, nitrogen is 0.01 concentration, right? M. Because 0.01 moles divided by 1 decimeter means 0.01 mol dm minus 3. That is the concentration. Right? So reaction quotient is something that we calculate similar as the equilibrium constant, but before the equilibration, right? Before the equilibration. So if I calculate the initial QC value, reaction quotient, I have explained this many times now. We had a discussion in the past paper in the essay part as well. So here my initial QC will be 0.4 squared, because there is a stoichiometry 2, divided by 0.1 cube multiplied by 0.01. So here it will be 0.16. Here this will be 10 to the power minus 3. And here it will be 10 to the power minus 2. So basically my initial Q here 0.16, 10 to the power minus 5. If it goes up, it will be 10 to the power plus 5. So it will be 0.16 times 10 to the power 5. So I can write down this as 16 into 10 to the power 3, or 160 into 10 to the power 2 mol squared minus 2 dm6. Okay, ml minus 2 dm6. So you see here my initial Q value, the reaction quotient at the beginning, when the reaction starts, when the equilibrium starts, is around 160. Now this, after equilibrium, the value is 2 into 10 to the power 2. So you see here there should be a drop from 160 to 2, which means initially the equilibrium is shifted towards the ammonia side. Why? Because the QC value is very larger here, 160, because we get the product of this divided by product of this, right? However, during the equilibration, you see here, this value is decreasing from 160 to 2, which means during the equilibration. So now I am writing here, during the equilibration, the equilibrium is shifted more towards the left-hand side, giving more and more hydrogen and nitrogen from ammonia. And finally, it will reach the equilibrium. Okay, now let's go through these statements. Initially, QC is larger than KC. So you see here, QC is larger than KC. And ammonia starts to produce N2 and H2 gas, and the system reaches equilibrium. You see here, QC is large, and during the equilibration, this the equilibrium is shifted toward the left hand side. It gives more nitrogen and hydrogen from ammonia. So this statement is correct. Initially, QC is lower than KC. So this is wrong. Initially, the QC is lower than, this is also wrong. Right? Initially, QC is greater than KC. Yes, correct. N2 and H2 react to form NO3. No, I told you NH3 is giving N2 and H2. So this is also wrong. So the only answer that is correct is A. So the answer is first one. Okay, so you understand how we determine this type of, how we tackle this type of question, right? So try to understand this.